the die, and what do you expect? Any number from 1 to 6, each occurring with probability 1/6. In the first program, we investigated a way of looking at probability as a long-term frequency. And in this unit, we've shown how the expected value of a random variable can also be seen as a long-term result. In this case, a long-term average. For this die, let the random variable be the number showing when we throw it. What is the expected value? Well, it's 1/6 times 1 plus 2 plus 3 plus 4 plus 5 plus 6. And you've already shown that to be 3.5 in the tape section earlier in the unit. What we're going to do now is rerun the throws from that first program. This time, we'll plot the average of the numbers we get against the number of throws. And you can see the calculated value of 3.5 marked in. You may remember that, first of all, I did 6 throws. Let's see those again. A 1. We've had a 5 and a 1. And now a 6. And another 6. A 5. And 1. But settling down, we'll need a large number of throws. 5, 3, 4, 4, 4, 1, 5, 1, 2, 5, 5, 6, 2, 1, 4, 3, 3, 6, 4, 5, 6, 3, 3, 3, 6, 4, 5, 4, 1, 1, 3, 1, 4, 3, 6, 2, 1, 5. Indeed, as you can see, the average is settling down nicely, not far off the 3.5 mark. 1, 1, 3, 6, 6, 4, 4, 6, 6, 6, 5, 1, 6, 1. We could do this for any expectation. The variance, for example, is an expectation. You've already calculated that as 35 over 12. You can see how the variance settles down after the same 60 throws. Now, with the concept of expectation clearly in your mind, we're going on to look at a practical problem where expectation will prove to be very useful.
Friedreich's ataxia is a rare disease which affects the nervous system progressively. It becomes manifest in early childhood and is fatal. There's no doubt it's inherited, and what's of interest is the actual genetic mechanism behind it. It's a rare disease, but we do have some data, collected by Sjogren in 1943. His data starts with families with 2 children. 8 families observed, that's 16 children in all, of whom 9 were affected. Next, families of 3 children. 11 families gave 33 children, 14 were affected. Families of 4 children, 9 families to give 36 children, 11 affected. And the data continues for families with 5, 6, 7 children, and so on. It goes as far as observing one family with 12 children, of whom 6 were affected. It's the mechanism of transmission of the disease we're trying to get at, and we're going to have to get that from this data set. But how? First, we set up a theoretical model based on what we suppose the mechanism might be. Then, we check it out against that data. And how can we do that? We can use the theoretical model to calculate expected values for the numbers of affected children, and then we can compare those with the observed values. If the comparison is good, then our assumptions for the original model of the mechanism are at least on the right lines. But first, what might that mechanism be? Genetic mechanisms are, in a very broad sense, a bit like a game of snap, in that genes combine in pairs. I'll show you what I mean. The man and the woman at this table each have special cards through which the light is shining. In fact, each of these is made up of 2 cards. If I combine one of the man's cards with one of the woman's, either the light shines through or it doesn't. You'll see later that these cards represent genetic coding. Each man and each woman have a gene pair, and an offspring will have a gene pair with one gene from each parent. So, let's look at some reproduction. Here are one pair of parents, and they're going to simulate building a family. So that's a gene pair for the first child. And the light shines through. The gene used is being picked at random. And it's only when we put them together we see what we've got. Now, I want you to imagine that when the light shines through, that represents a healthy child. And when it doesn't, we have an affected offspring. Out of a family of 5 children, 1 is affected. Now, how does this come about? Each parent has a pair of genes. Now, I can't distinguish one from the other, so I'll label them. If I were to take the man's first gene and combine it with either of the woman's, no affected offspring. Now the other male gene. Again, the light shines through, unaffected. But on this one, we have an affected child. So, out of 4 possible combinations, the genetic codes are such that only 1 out of the 4 results in an affected child. So this child will have a probability of 1/4 of being affected. Now, here's a family of 6 children, 1 affected and 5 unaffected, each one of which was created with probability of 1/4 of being affected. So according to this genetic model, the random variable representing the number of affected children of a family of size 6 is binomially distributed with p equals 1/4. So the probability of 0 affected children is 0.18, of 1 is 0.36, of 2, 0.30, of 3, 0.13, of 4, 0.04, of 5, 0.004, of 6, 0.0002.
Having obtained the distribution, we can go on to determine the mean. We could do this in a number of ways, but I'm going to calculate the mean using the probability generating function, or PGF. This is the distribution. To get the PGF, we multiply the probability of 0 by s to the power 0, add to that the probability of 1 multiplied by s to the power 1, add to their sum the probability of 2 times s squared, and so on. Using the binomial theorem, we can write the result as 3/4 plus 1/4 s all to the power 6. Or, for general n and p, it looks like this. Having got the PGF, calculation of the expected value of x is quite straightforward. Remember that for any random variable, the PGF is the summation of s to the power x times the probability of x over all values of x. If we differentiate with respect to s, we find that pi dashed of s is this expression. And so if we put s equal to 1, we see that pi dashed at 1 is the summation of x times the probability of x. And this, of course, is the expected value of x.
For a binomial distribution, the random variable x takes on the values 0, 1, 2, etc. as far as n. If I put in n equals 6 and p equals 1/4 and work out the expected value of x, it turns out to be 1.5. You can check that out for yourselves afterwards. That's simple enough. It's not particularly surprising then that this family had 1 affected child. However, we're not yet ready to look at the data. Things aren't quite as straightforward as this. Let me show you why. Supposing I can do what in real life just isn't possible, which is to determine the coding of individual genes. Using this analyzer, I can determine the coding of an individual card. First, we'll look at the father's cards. Until I use the analyzer, I can't tell any difference between them. But look. And now, the mother's. I can tell which two to use to simulate an affected child. And to do it, both parents have to carry that coding. Let's look at another family. They don't have any affected children. He carries the disease-transmitting code. But but the mother doesn't. So there's no possibility whatsoever of an affected child. The same would apply if neither were carriers. So, for the disease to be transmitted, both have to be carriers. Here's another family with no affected children. The father's a carrier. But wait a minute. So is the mother. This means that although they haven't had any affected children, they could have. They've been lucky. Now, for this simulation, I can always get the analyzer to detect which parents have the possibility of an affected child. But in real life, no such gene detector exists. So there's no way we can distinguish these parents from all the other parents with unaffected children. We just can't know which families are at risk until they've already produced at least one affected child. Our original data set had this property, at least one affected child.
So our random variable x, which is the number of affected children in a family, can only take the values 1, 2, 3, and so on, but not the value 0. One thing is certain, it can't be binomially distributed. But we can obtain its distribution by a simple modification of the binomial. We must first remove the first bar. This is the probability that x equals 0. It's perfectly reasonable to leave the other probabilities in the same relative proportions. But the trouble is, they don't add up to 1, so they don't constitute a distribution anymore. What they do add up to is 1 minus the probability that x equals 0. Now, the probability that x equals 0 was q to the n, so that's 1 minus q to the n. To keep them in the same proportions and to get them to sum to 1, we simply use 1 minus q to the n as a scaling factor. Each original probability is now divided by 1 minus q to the n. What that means for the general expression for the PGF is that we start with the binomial PGF, subtract the old coefficient of s to the power 0, that's q to the n, and divide the result by our scaling factor 1 minus q to the power n. Just to check that this is a true PGF, we can put s equal to 1 and see whether we get pi of 1 is equal to 1. Well, when s equals 1, this bracket gives q plus p to the n, but q plus p is 1, and so pi at 1 is 1 minus q to the n all over 1 minus q to the n, which is indeed 1. And what is the expected value of this new distribution? Well, we have the PGF available, so to find the expected value, we need to differentiate it and put s equal to 1. Here's the PGF. Differentiating with respect to s gives us this second line here. And so if we put s equal to 1, we find that the expected value of x equals pi dashed at 1, which comes to n times p over 1 minus q to the n. The details of this are in the text.
I can use that formula to calculate the expected number of children for any family size on the hypothesis that p is a quarter. For example, the expected value for a family of 6 children comes out as 1.82. In our original data, there were 7 families with 6 children. The expected number of affected children is 1.82 per family, giving 7 times 1.82, which is 12.8. Compare that with the observed value of 15. We can repeat this for all the other family sizes, still keeping p as a quarter. overall, there's quite good agreement between the observed and the expected values. Later in the course, you'll see how, formally, to test the quality of such a correspondence. And in fact, you'll find it's very close. This tells us that the modified binomial distribution, with p equals 1/4, fits the observed data very well. It means that the original assumptions about the genetic mechanism, which led us to the theoretical model, are acceptable. And so, on the one hand, it offers us a means of calculating probabilities, perhaps in a genetic counselling context, and on the other, it provides evidence on which a geneticist might base his understanding of the disease.
There'll be another programme for probability and statistics on the 21st of April at 5 to 2.
Colleen